Alrighty, so we are going to continue with our discussion of Chapter 9. This time we're going to talk about Section 2, which involves mass calculations. So last time we talked about mole ratio and how we can relate the moles of different compounds within a reaction to each other. So now we're going to take that and the stoichiometry we've already learned from Chapter 6, so molar mass, atomic mass, Avogadro's number, and we're going to put all that stuff together. Okay. So when we're doing mass calculations, we want to convert our mole amounts to gram amounts. So in the end, we're trying to find a mass, but in order to convert between compounds, we need the number of moles. And so that's why we say that we're combining mole ratio with things like atomic and molar mass. And so we use molar mass, a balanced equation. Balanced is so important, and the mole ratio. Okay, so let's look at an example. So we have this propane. And we want to know what mass of oxygen is going to be required to react with 44.1 grams of propane. Ugh, I'm in trouble talking today. Okay, so our first step is to balance the equation. So we have C3H8 plus O2, and that's going to CO2 plus H2O. Well, we did this example in Section 1, and so I know that we're going to need a 3 and a 4, and that makes 10 oxygens, and so we need a 5. Okay, so that's our first step. I would also write what you're trying to solve for. So we're looking for grams of oxygen, and we have 44.1 grams of propane. This is the organic compound propane. Okay, so step 2, we have balanced our equation, which, like we said, is really important if you're going to do mole ratio. So next, we need to convert grams of propane to moles, because the balanced equation deals only in moles. This is how we're going to get mole ratio. This is how we convert between compounds. Remember we said last section that the only way to convert between compounds is mole ratio. So we've got to get our grams to moles first. Okay, so we're going to start with our 44.1 grams of C3H8. I want grams of C3H8 on the bottom, and I know that according to molar mass, it's grams per 1 mole. And let's calculate the molar mass of C3H8. So I know I have 3 times carbon's mass plus 8 times hydrogen's mass. And let's just calculate that out real quick. 3 times 12.01 plus 8 times 1.008. If you want, you could follow along on your calculator. It's good practice, and then you know that you're doing it and actively watching the video and learning, and that's always a good thing. So if we add those up, we get 44.094, and so that is our number of grams per mole. Okay, and so we could solve for that. So 44.1 divided by 44.094, and that gives me almost exactly 1. So now I've gotten to moles of propane. Now I can use my mole ratio. Okay, so now I want to use the equation and the moles, the balanced equation, to determine the mole ratio, or the moles of oxygen needed. So we're breaking this down into each individual step. Normally I would continue this all in one long stoichiometry problem, and we will do some other examples of that. But just keep that in mind. We're kind of breaking it up into steps. Okay, so let's take our 1 mole of C3H8. And we know, according to the balanced chemical reaction, that for every 1 mole of C3H8, there are 5 moles of O2 that we need. So I want my C3H8 on the bottom. 5 moles of O2 goes on top. Really don't need a calculator for this one because it's 1. And so this comes out to 5 moles of O2. Not always will there be such a nice number. So it is good to write this stuff out. Okay, so now we've got moles of oxygen needed. But in the end, we want grams. So we've got one more step to go. Okay, so our fourth step is to convert our moles to grams. So let's take our 5 moles of O2. Okay, to go between moles and grams, I need molar or atomic mass. And so for O2, it's just 2 times oxygen's atomic mass, which is 16 or 15.99. So I know for every 1 mole of O2, 2 times 15.99 is 31.98. So that's the number of grams in the molecule O2. Because it's on top, I'm going to multiply it by 5. So I get 159.9 grams of O2. Okay, my last step is, again, to look at significant figures. No, they are never going away. Okay, so we have 3 significant figures in the problem. I want 3 in my answer. This 9 will round this 9, so I'm actually going to get an answer of 160 grams of O2, but I do want 3 significant figures. So there are 2 different ways to express 3 significant figures. I can put a decimal after the 0, and now I'm making it count. Or I can write it as, 1.60 times 10 to the second. And so I'm still showing 3 significant figures, and it's the same answer. So either of those options will work if you run into a problem like this. Okay, so let's try a couple other examples. We can also do math calculations involving scientific notation. This should not be a big deal, especially since you can put it in your calculator. So let's try combining all those steps into one. Okay, so we have solid lithium hydroxide is used in space vehicles to remove exhaled carbon dioxide from the living environment. So the products are solid lithium carbonate and liquid water. And so we want to know what mass of gaseous carbon dioxide can 1 times 10 to the 3rd grams of lithium hydroxide absorb. Well, we know the first step is to write the equation, so let's do that. So we have lithium hydroxide, and I know lithium's charge is a 1 plus and hydroxide's 1 minus. So 1 to 1, that compound is written correctly, and it's a solid. And we know that it is absorbing exhaled carbon dioxide, so that tells me that the carbon dioxide is a gas. And we know our products are solid lithium carbonate. Well, I know carbonate is a 2 minus. This is our polyatomic. Lithium is still the 1 plus, so I need 2 lithiums to make this a neutral compound. And our other product is liquid water. Oh, and this was a solid. Okay, so we've written our equation. Let's get our information, and then we'll balance it. Let's see. What mass of gaseous carbon dioxide? So we're looking for grams here. And we have 1 times 10 to the 3rd grams of lithium hydroxide. So now let's balance. Let's see. I've got 2 lithiums on the product side, so we'll just put a 2 up front. Another way to write water is HOH. I don't know if that's going to help us in this case, but you can write it either way. Let's see. Now my carbons look okay, so let's just add everything up. So we've got 2 oxygens in the lithium hydroxide and 2 in the carbon dioxide, so that's 4 total. And we've got 3 in the carbonate and 1 in the water, so that's 4. So that looks okay. Let's check hydrogens. We have 2 hydrogens on the reactant side, 2 on the product side. We did not need to write the water like that, so I think we just needed the 2 here, and I think it's balanced. Okay, so let's try putting all those steps we talked about in the previous example into one big step. So we're going to take our 1 times 10 to the 3rd grams of lithium hydroxide. This is where writing your units and writing all your compounds is going to be really important, because now we're switching between compounds, and if you don't put your unit labels, you're not going to know which is which. Or at least this makes it easier, I think. A little bit of extra writing at the beginning makes for a much easier process at the end. Okay, so we know that the first step after balancing was to convert our grams to moles. So we want to convert grams of lithium hydroxide to moles using the molar mass. Okay, well the mass of lithium is 6.94, plus we've got an oxygen, which is 15.99, plus 1 hydrogen, 1.008, so we get 23.938 grams of lithium hydroxide. Okay, and if you are feeling confident about this, you could just pause the video, try it on your own, and then see if you got it right, because chances are you're probably going to get it right. So that's not always a bad idea either. Okay, so once we have number moles of lithium hydroxide, then we can use our mole ratio to convert between compounds. And so I know, according to the balanced chemical equation, that for every 2 moles of lithium hydroxide, and it goes on the bottom because I want my units to cancel, we need 1 mole of CO2. And then our next step was to convert moles to grams, so we can get grams of carbon dioxide. So we're going to use the molar mass of carbon dioxide. So I know for every 1 mole of CO2, let's get its molar mass. Carbon is 12.01 plus 2 times oxygen's atomic mass, because there's 2 oxygens in CO2. And we get 43.99 grams. So if I look back at my units, my grams of lithium will cancel, my moles of lithium will cancel, my moles of CO2 cancel, and I have grams. So here I used molar mass of lithium hydroxide. Here I used the mole ratio. And here I used molar mass of CO2. So that's kind of the pattern or the steps that you're going to follow. So now let's calculate the whole thing. So we're going to start with our 1 times 10 to the third. And I'm going to put this in parentheses because it is in scientific notation. So we have, where's a good spot to write this? How about up here? So we are starting with 1 times, let's see, 10. Where's the pen? There it is. Third. And then we're going to divide by 23.938. And we put this part in parentheses. And then the 2 is on the bottom, so we're going to divide by 2, which is right here. And then our 43.99 is on top, so we're going to multiply by 43.99. So let's do that real quick. So divide by 23.938. Again, you could also do this along with me. It's not bad practice. Okay, and we end up with 918.83, so let's get that down here, 19.83, this is grams of CO2. Our last step was to do, not scientific notation, significant figures. So if we look at what we're given in the problem, I've got 3, 1, 2, 3, so 919 grams of CO2 will be absorbed for every 1 times 10 to the third grams of lithium hydroxide. Okay, so putting all those steps together, I think this is the better way to do it. You have, less transferring of numbers. You can see how all your units cancel out. Let's try one more. Let's say we're comparing 2 reactions. So let's do a practical application. So given 2 different antacids, which one can consume the most stomach acid? We have a gram of sodium bicarbonate or a gram of magnesium hydroxide. These are the main active ingredients in different antacids. Okay, and so here's our 2 reactions. Okay, and so I've actually got them over here. So we've got 1 gram of this antacid, and we want to know how much hydrochloric acid it can neutralize. So we're looking for grams of HCl. And let's just do a quick check. This already looks balanced to me, so that's nice. So let's start with the 1 gram of sodium bicarbonate. Okay, remember, if we're going to convert between compounds, the first thing we need to do is get to moles, so we can use the mole ratio. And again, if you want to pause this and then try it on your own and check, that's not a bad idea. So let's see, we need for every 1 mole of sodium bicarbonate, let's add up that molar mass real quick. Sodium is 22.99, we've got 1 hydrogen, we've got 1 carbon, and we've got 3 oxygens. And so that's 84.008 grams of NaHCO3. Okay, now that we're in moles, we can do the mole ratio. Well, everything's 1 to 1, so that's pretty nice. So for every 1 mole of NaHCO3, there's 1 mole of HCl. And the last thing we need is grams of hydrochloric acid. So for every 1 mole of hydrochloric acid, I need the molar mass. So I have my 1.008 from hydrogen plus my 35.45 from chlorine, and that is 36.458 grams. Okay, so I've used molar mass of sodium bicarbonate, molar ratio, molar mass of hydrochloric acid. So let's take our 1 divided by 84.008. 1 to 1, so we don't need to multiply or divide anything there, and then times 36.458 because that's on top. So we get 0.43398 grams of HCl. Looks like we had 3 significant figures, so 0.434 grams of HCl for the sodium bicarbonate. Now let's do the other antacid and then compare our values. So magnesium hydroxide, again, we start with 1 gram. We're looking for grams of HCl. Let's just make sure this is balanced. This one does not look balanced because we have 2 chlorines and only 1. So I'm going to put the hydrogen there, or the 2 there, sorry. Writing water as HOH here is going to be helpful because we have our hydroxide and our hydrogen. Actually, if you look, this is an acid-base reaction because we have the acid and the base producing the salt and the water. So since we put the 2 here, we have 2 hydrogens 2 hydroxide groups. So put a 2. Now I think it's balanced, so let's start with our 1 gram of magnesium hydroxide. Okay, again, the first thing we need is the molar mass. And we're going to have to take that hydroxide and multiply it by 2, so let's do that first. So the oxygen plus hydrogen. And again, if you want to pause and try this on your own, that's a good idea. And then we're going to add magnesium in. So I get 58.306 grams of magnesium hydroxide. Okay, so now I'm in moles. Okay, my grams have canceled. Now I need to use my mole ratio. Well, from the balanced chemical equation, I can see that for every 1 mole of magnesium hydroxide, there are 2 moles of hydrochloric acid. And then we need, so now we're in moles of hydrochloric acid. So now we're going to use molar mass to get to grams. So for every 1 mole of HCl, oh, I forgot the molar mass of hydrochloric acid, 35.45 plus 1.658, 36.458. Okay, so we went from grams to moles, mole ratio, moles to grams. So now let's just calculate. So my 1 divided by 58.306. 2 is on top, so I'm going to multiply. 36 is on top, so times 36.458. And I get 1.25057, 3 significant figures. 1.25 grams of HCl is neutralized with the magnesium hydroxide. So now let's see. We had 0.434 with the sodium bicarbonate and 1.25 with the magnesium hydroxide. So this is what I would call, based on straight up same quantity, the more effective antacid. So hopefully these examples have helped you. Try some of the homework, and if you have any questions, please ask. But please remember that it's really important to actively watch these videos. If you're just sitting there, maybe spacing out while I'm doing all these examples, I don't know how much you're actually gaining. And so it really is important to maybe watch a couple, but then pause it and try on your own. And then, check and see if you got it right, because that's really, going to be good practice for you. That's how you're going to start applying the concept. Okay, so have a good day.